Hello, my name is Lucy Ankers and I'm a transport modeller. In this short presentation, I'm going to give you a brief overview of transport modelling. So that's going to include what it is, why we do it, and what it can be used for. So just to start off, I'll tell you a little bit about myself and how I ended up in transport modelling. So at school, I studied maths, physics, and geography, my A levels. And then I went on to study natural sciences at Durham University. And natural sciences is a mixture of maths, geography, and earth sciences. At this point, I was thinking about potentially having a career in environmental sciences, but to be honest, I still didn't know exactly what. It was only in my third year when I did a dissertation in flood risk modelling that I thought potentially something in modelling might be right for me. As part of my dissertation, I developed a model in MATLAB to explore and predict the relationship between flooding and flood events and urbanisation in a catchment area. And I really enjoyed using data to be able to predict future events. So this gave me sort of an indication that, maybe that's something I would like to do for a career. In my third year, I applied for a graduate scheme at WSP, who are an engineering consultancy who cover a wide range of disciplines, anything from bridges and energy to coastal erosion and transport. It's a huge mix of topics. I just happened to be interviewed by two transport modelers who thought I would be well suited to the role, who enjoyed learning about my dissertation and thought that I had a lot of transferable skills that could be used to model traffic flows instead of water flows. So that was nearly 10 years ago now. I joined WSP and spent, I think, 6.5 years there. And then I've spent the last 3 years at Jacobs, who are another engineering consultancy firm. So on to transport models in a bit more detail. What are they? So transport models are computer simulations of transport systems, and they can be spreadsheet models or they can use specific transport modeling software. And we've got some screenshots from some of this transport modeling software later on in the slides. You can have highway, public transport, pedestrian or cycle modeling. And you can have multimodal models which have components of each of these. And then you've got a huge variation in the scale of transport models as well. So for example, you could have a highway model of a whole region, for example, the southeast of England, or you could have a pedestrian model of a town centre bus station. So there's a huge range in both the mode of transport you're modelling and the scale at which you're modelling. So next question is, why do we need them? There has been a big emphasis on climate change and sustainability in government over the last few years, and transport models can be used to anticipate future problems and try and fix these problems. So, for example, if we build 100 new homes here, what is the impact on the highway network in the surrounding area or on this particular junction? They can also be used to test potential solutions. So if you've got a problem that you know about already, like poor air quality in a town centre environment, how can we try and improve that air quality? Should we build a bypass so that traffic avoids the town centre? Or should we introduce a clean air zone with tolls? For example, London's ULEZ, which is ultra low emission zone. And then finally, we can use them as an evidence base for decision making. So if we apply for government funding to try and improve our transport network, is this going to be a good investment for government funds? These are the main reasons. They're sort of everyday reasons why we use transport models. There are some slightly more niche uses as well. So, for example, during COVID, pedestrian modelling was used to try and simulate transmission of the virus in different scenarios. So, depending on how many people had the virus and how quickly it was spreading, the government could introduce measures to deal with it appropriately. In terms of the types of transport model, I touched on this briefly earlier. You've got different scales. So we've got a strategic model is our biggest model. And this is the top image on the left. And this can be of a whole region or a county. Then we have micro simulation models, which are smaller areas, potentially a town centre or a particular road corridor. And then the smallest level is the junction models, which is a specific junction or a group of junctions. And then for pedestrian modelling, for example, or public transport modelling, it's the same. We can model the whole network, or we can model right down to individual rail station platforms, like the bottom picture. And the level of detail tends to increase as the size of the model decreases. So if we had a strategic model of the whole country, we obviously can't model each junction in the same amount of detail as we could if we had just a single junction or two, because the run times and the data would just be far too big for anything to be done efficiently. So there are two main components of transport models. There's the supply, which is how people get from A to B, and then the demand, which is the trips that are actually being made. So this slide just shows a brief overview of some of the supply components which build up a transport network. So we've got the nodes, which are the junctions. So this would be information on whether it's a signalized junction or a roundabout, if there are any blocked turns. So for example, you can only turn left out of the junction, the right turn is blocked. It also would have details of the junction geometry, for example, the number of entry lanes, if there's a pocket turn or a flare. And then if it's a signalized junction, the information for the signals. So the length of the green times, the intergreens, which movements are allowed when, and so on. We also have the links, which are the roads. And these will have details on the length, the speed limit, the capacity, any sort of characteristics like this, which will affect how people travel. Thirdly, we have the zones, and this is where trips start and end. So they could represent groups of houses, or for example, a business park, any of the sort of sources of traffic in the network where people might want to make trips from and to. Then we have our connectors, which is how these kind of does what it says on the tin. These connect the zones to the network, so and allow trips to access the links from the zones. And then if it's a PT model as well, we would have information on the stops, so bus stops, rail stations, and the services as well. So the different bus routes, for example, including the timetables. Then the second component is the demand. And this is entered as a matrix of trips. so from zone to zone, as shown on the screen here. And these demand matrices include all the information about travel patterns, so where people are traveling from and where they're traveling to. A key source of this data that we use when building transport models is mobile network data. And this is basically the data that mobile phone operators receive when a person moves from a particular location to another location. And how it works is the country is divided up into different areas, which are each served by fixed location towers. And these towers provide the area with the network coverage, so how you get signal for your phone. And as a mobile phone moves from one area to the next area, they communicate with the corresponding towers. And it allows mobile phone operators who get this data to build up a picture of travel patterns. So it's a great way of getting a huge sample size, but there are some problems associated with it. For example, if 20 phone signals suddenly move from one area to the next area, is that just 20 people on a single bus moving from one area to the next area, or is that 20 people in 20 separate cars? So you can see that there is obviously great source of data, but there are limitations, and there is processing that we have to do on that data before we can use it. We tend to do this by merging it with other sources, for example, census data, to try and get this level of detail. And then we also need information on the types of vehicle and the journey purpose as they travel in different ways through the network. So, for example, HGVs, which are lorries and trucks, might be more likely to use motorways than rural roads because they're more attractive for those types of large vehicles. And leisure travellers, so people travelling for a day trip or to the shops, might be likely to use a more scenic route, for example, than someone who is travelling for business. So all of this information is included in our transport demand matrices. So once we have the supply, which is our network, and the demand, we can put them together, and this is called running an assignment. And once you've run your model, you can extract different types of outputs, for example, flows, delays, and journey times. So it's very important that transport models are able to accurately represent existing conditions before we can start using them to test scenarios. And this involves collecting a lot of transport data. And this could be flow data, this could be journey time data. And with this data, we undergo a process of calibration and validation. And this is comparing modeled and observed data and adjusting the model to make the model results more accurate. So, for example, comparing the modeled flow along a particular road and the observed flow from a survey count on that road, and seeing if they are similar or if our model is actually not doing a very good job at representing traffic flow along that road. And depending on the size of the transport model, this can mean getting a huge amount of data. So this slide shows the extent of the data we had to collect when validating a model for West Essex. So the area of interest is shown in green, and then all the dots are different traffic counts that we collected. And the red lines are journey times that we carried out. So, to try and build up the most accurate picture of existing conditions in the modelled area that we had to try and replicate. We also had a PT, a public transport element to this model. So we carried out passenger counts at rail stations and key bus stops. So once we've built our transport model, collected our data, calibrated and validated it, so we think that we've got a base year that represents existing conditions, we can start thinking about the future. So we can develop a do minimum scenario for a year in the future, for example, 2050. We can add in the planned infrastructure schemes. So if we know that there's going to be a new road or planning permission has been granted for a new junction, we can add that in, update our network, and we can also uplift our demand matrices to include traffic growth between now and 2050. So we get this from population and job numbers from local authorities often, and then the government also has a database of expected growth. So this gives us a sort of do minimum scenario of our most likely case for the future year conditions. Then we can create a do something model. So this is the same as the do minimum model, but we will make a change to include the particular scheme or development that is going to be tested. So we will add in 200 new houses in a certain location, or we will add in a new bypass. We can then run both models, run the do minimum, run the do something, and compare the results. So this is shown on our next slide here. So again, we can look at things like the flow difference between the two models, the delay difference, and junction performance. So here, for example, what you can see is the traffic flow difference plot, and green shows an increase of traffic and blue shows a decrease in traffic. So what we've actually got here is we were testing a new bypass in Kent, and the green shows all the traffic diverting onto the bypass away from the existing high street. So now a bit more about what we call transport appraisal, which is how we can use transport models to demonstrate if a particular scheme represents good value for money. So the government has a pot of money for transport infrastructure improvements, and local authorities can apply for funding to fund their schemes, basically, but they have to demonstrate that their scheme is a good investment. And the way that you can do that is use transport models to calculate the benefits from your scheme. So this could be journey time savings, accident savings, carbon savings, and you can monetize these benefits. So, for example, if building a new bypass saves 3 minutes of travel time per person because it reduces congestion, and 1,000 people use that road a day, and each of those people's time is worth 50 pence per minute, that would save 3 minutes times 1,000 people times 50 pence per minute. So that would save £1,500 a day. Another example with the carbon emissions. So if you're reducing congestion, you're reducing emissions. For example, each ton of carbon emissions that you reduce is worth £2 cost to the environment, for example. So you can work out the total benefits that your scheme would save and compare this against the scheme cost to calculate what we call a benefit cost ratio, or BCR. And the table on the right here shows that the government has different value for money categories. So if you have a BCR greater than or equal to 4, it represents very high value for money. and you're much more likely to get funding for your scheme versus if your BCR is less than 1 and it's a poor value for money. So on to our final couple of slides now. This slide touches on some of the challenges that we're faced with in transport modelling. One of the main areas is uncertainty. And I've talked a bit about how we use transport models to solve problems in the future, but the future is very uncertain. Things we can't predict, for example, population growth. We can give it our best estimates based on the information that we have available, but there could be things that change. Will people continue to live in the same areas that they currently live in? Will they continue to work in the same areas they currently work in? There are lots of things that can change travel patterns. A key example being COVID. So since COVID, a lot more people work from home on a regular basis. There are also new technologies, for example, Uber and ride-sharing apps. Will this result in lower car ownership in the future and therefore less trips made by car? So all of these things will affect our transport models. So there are lots of challenges, lots of things that are always changing, but it does keep it fast-paced and interesting. So the last slide is just a quick wrap up of whether transport modelling might be a good fit for you. So if you enjoy working with numbers and enjoy problem solving, most of our projects are about solving the problems that our clients come to us with. We work with a lot of data, a lot of Excel. Then it's probably something you could think about. Some of my favourite things about working in transport modelling, you get to work on large, quite exciting projects, and these often shape the world around us. Like, it's very exciting to see a road being built which you've actually helped secure funding for. And then finally, no two projects are the same, which keeps it interesting. Thank you for listening, and I hope you enjoy the rest of your day.